Now, another concept that some of you may already know and some of you don't is electricity. What exactly is electricity? And electricity is moving electrons. So if you remember back in high school physics, you had your atom. And inside the atom, you had the nucleus, which is positively charged. It has protons in there that are positively charged. And then outside that nucleus, we have electrons basically spinning around the outside of the atom. And those electrons are negatively charged. And those electrons are what create electricity. The electrons moving from one particle to the next is actually electricity. So basically, electrons in motion is electricity. And so on your wire or conductor or whatever you're transferring your electricity with, all those little atoms and particles inside that matter that you're transmitting your electricity through, it's just the little electrons jumping from one atom to another inside your copper wire or whatever you're using to transmit the electricity. So that is what electricity is moving electrons. Now, a basic circuit, those electrons have to have a path to follow. So an electric circuit is the path over which the electric current can flow. So if we look at our two diagrams here, we have the one where everything's turned on, and we've got our battery, and we'll talk more about batteries and how they work, but we have a battery, and it has a negatively charged pole and a positively charged pole. And from our negatively charged pole, there's extra electrons in there, and our positively charged pole has a place for those electrons to go. And electrons always want to go where there's a place for them, where they're missing electrons, where it's positively charged. So these electrons are going to look and they're going to see a way to get there. They're going to see wire running through here, all the way across here, and up to here to that positive side. So they see that pathway and they're going to follow that pathway. So these electrons are going to go from this side, they're going to pass through, and they're going to cut over to the positive side until so many electrons have moved over that it's no longer negatively charged over here, which then your battery's dead. So as they flow through this circuit, they're going to power this light bulb right here. So you can see the light bulb is on. Now, if we look at this circuit, it's exactly the same, except we have this little switch over here, which we have the switch here too. It's just the switch is in the on position so that the power can flow through. Now in this diagram, the switch is in the off position. So our little electrons over here can't see a full pathway to get to the positive because our path is broken. Our circuit is open. So this light bulb is not lit because the electrons, if they don't see a path to get all the way to the positive, they're not going to go anywhere. So these electrons are just going to sit in this battery and wait until this switch gets closed and they have the pathway like they do in this drawing. So when we talk about circuits being on or off, we don't always use the terms on and off when we're talking about electronics. Oftentimes we use the wording that the circuit is closed or the circuit is open. When the circuit is closed, then you have a full pathway to get from negative to positive, and your equipment is going to be energized as the electrons flow through it, and your little light bulb is going to be on or whatever other electrical load you have in here. Now, if your circuit is open, your switch is open like this, now there's not a full path for these electrons to go because they're going to start here and they're going to stop here, and they don't see a full path to get to the positive side. So they're not going to go anywhere, and your equipment will not be energized. So when the circuit is open, no current is flowing. And when the circuit is closed, the current will be flowing. So that's the basic circuit, and when we're talking about an electrical circuit, it's just a path for those electrons to move on. And if the circuit's closed, they can go, and if the circuit's open, they're not going to go anywhere. So now we need to cover a few basic definitions that you need to know. Now, first of all, when we talk about electricity, we're often talking about current and voltage. So current is the rate of flow of electrons. And current is measured in terms of how many electrons are flowing. And when we talk about current, we measure it in amps. And 1 amp is a whole lot of electrons. I believe this number is way, way, way too high for anybody to reasonably use, which is why they say it's 1 amp instead of having to say it's, I think that's 6 quintillion, but I'm not quite sure. But it's a ridiculous number of electrons. So when we talk about 1 amp, keep in mind that there's a lot of little electrons that make up that amp. And the other thing about current is that it travels about 180,000 miles per second, or 648 million miles per hour, which is almost the speed of light. So electricity does take time to get from point A to point B, but more often than not, it's so fast you can't even, a human can't perceive such a small amount of time for the electricity to go along a 100-foot run of wire or something like that. So it does travel about the speed of light, which for the most part, when you turn something on, it's going to be instantly, the whole circuit's going to be instantly energized, because it's going to happen so fast that you're not going to have a chance to even blink. 180,000 miles per second is very fast. Now, the other thing to remember about current is that it's represented by an I for intensity. We're going to get to some formulas here, and they're always going to put in letters for things like current and voltage. And so we have to remember what letters they're going to use. So sometimes it'll be A for amps, sometimes it'll be current, and sometimes it'll be I, which stands for intensity. So whenever you see an I in a formula, you're going to think immediately that that's current, which is going to be amps. Now, voltage is another term and another way to measure electricity. And voltage is the pressure that forces the electrons to flow. So when they talk about hydraulic equivalents of things, current is the rate of flow, and voltage is the pressure that pushes the current. Voltage is often represented by an E for electromotive force, which is what they used to call it back in the old days, when back in the 1800s, when electricity was just something to play with in your basement if you were a scientist. So E will represent voltage in a lot of formulas. Sometimes they'll put the V in there, and sometimes they'll put an E instead. So you have to memorize that voltage is represented by an E sometimes. Now, the other thing about voltage is they call it the potential or potential difference. And the reason they call it this, and this is one of the things you'll have to learn in order to get through these NABCEP tests, is you have to learn to speak textbook. A lot of times we put things in more simple terms when we're talking or writing about this. But when you sit down to read the NABCEP questions, they are written in textbook, which sometimes seems like a whole different language. But the textbook way to say the potential difference is charge opposition between the two materials creates an electric field that provides momentum and direction to the free charge carriers, resulting in the flow of electrical current when the cell is connected to a load. Okay, so let's translate this and break it down a bit. So charge opposition between two materials. What we're talking about here is, remember that battery, it has a negative side and a positive side. That's charge opposition right there. We have one side that has extra electrons and one side that is missing electrons. So the extra electrons is the negative side, the missing electrons is the positive side. And the difference between those two, that's a potential difference. When we close that circuit, that's going to give us the pressure that pushes those electrons. So it's the difference from the positive to the negative that gives us the pressure. And a higher difference between the positive and negative will give us a higher pressure and a higher voltage. So, you talk about a regular battery being 12 volt, and sometimes we'll put together a battery bank that's 48 volt. It's just got more pressure pushing those amps through. And, excuse me, so we've got the two materials creating an electrical field that provides momentum and direction to the free charge carriers. Free charge carriers are the electrons we're talking about. They're charge carriers because they carry a negative charge, and they're free because they're extra. The negative side has extra electrons, so it's got free charge carriers bouncing around trying to find a home, and they'll end up finding their home on the positive side. So the difference, the opposition between the two materials, or the potential difference between the two materials, creates that field that provides the momentum and direction to the electrons, which results in the flow of electrical current when the cell is connected to a load. And that's basically talking about when there's a circuit path for the electricity to flow along. So that's why they call voltage potential difference, because it's the potential difference between the negative side and the positive side that gives you the voltage, and that voltage is the pressure that pushes those electrons. So that's current and voltage. Now, another thing we need to talk about with electricity is resistance. And resistance is the opposition to the flow of electrical current. So if electrons move easily from one atom to another in a certain substance, it's going to have a very low resistance. And if it is difficult for electrons to move, it's going to have a high resistance. So it's all about how easy it is for those little extra electrons to jump from particle to particle inside the substance. So some substances have low resistance and some substances have high resistance, and we'll talk about that more later. But basically resistance, the equivalent, the hydraulic equivalent of resistance would be friction. It's just resistance against the movement, or in this case it's resistance against the flow of electric current, which is those little electrons moving. So materials with high resistance have low conductivity, and materials with low resistance will have high conductivity. And resistance is measured in ohms, which is given with this omega symbol here. And Ohm was a guy, one of those scientists that was playing with electricity in his basement back in the 1800s. So some stuff is named after him, including Ohm's law, which we'll talk about in a minute. But right now, just know that resistance is measured in ohms, so you're going to look for this little omega sign, and anytime you see that, you know we're talking about resistance. And then often resistance is represented by an R, which thank goodness that R stands for resistance, so that's not too hard to remember. So now we've got I for current, we've got E for voltage, and then R for resistance. So resistance is the easy one. And then one other thing about resistance is that all electrical systems have some resistance, no matter what. Every little bit of wire, every piece of circuitry, every electronic component has resistance. So there's always resistance. It's just a matter of how much. Things that are, we say are highly conductive are going to have a low resistance. So Ohm's law defines the relationships between power, which is watts, voltage, which is voltage, current, which is amps, and resistance, which is ohms in electrical circuits. So Ohms sat down in his basement and fiddled around with electricity long enough to understand the relationship that these things had with each other: power, voltage, current, and resistance. And the basis of Ohm's law is that the current of 1 amp passing through a resistance of 1 ohm results in a potential difference of 1 volt. So that's the basis of Ohm's law, and there's quite a lot more to it as we go along here. So this is Ohm's law, and it's often shown as a wheel, just like this. And the things that you need to remember most are right here in these triangles, and I'll explain these triangles in a minute. But let's talk about this wheel here for a second. So the answer to these equations right here, these formulas, is voltage. So if I want to know my voltage on a circuit, I can either take I times R. Now, if we can't remember what I stands for, I put it down here. So this is something you want to memorize. I times R is going to be current, or amps, times R, which is resistance, or ohms. And that's going to give us volts. If we know the amps and the resistance of a circuit, we multiply those two together, and that tells us the volts. Now this P, you can look down here, P is watts, or power. Remember we just talked about that in great detail earlier. So we've got our power divided by our current, or divided by our amps, is also going to give us our volts. And then this one you don't need to know too much, but if you take the power, multiply it by the resistance, and take the square root, that will also give you the voltage. Now this side is, this is the resistance. So how do we find resistance? Well, we can take our volts divided by our current, or divided by our amps, and that will tell us our resistance. We can take volts squared divided by power, or watts, and that's going to tell us our resistance. Or we can take the power, or watts, divided by the current squared, or the amps squared. And then same thing here. If we want to know our watts, we can take our volts times our amps, and that's a huge one. I'm going to repeat it many, many times through this whole program. Volts times amps equals watts. Drill that one through your head. You can also take the current squared times resistance, or you can take the volts squared divided by resistance. And then if we're trying to figure out our current, or our amps, we can either take voltage divided by resistance, we can take power divided by volts, or watts divided by volts, or we can take our watts divided by resistance and take the square root of that. And these square root ones, you'll never have to do those ones for the NABCEP tests, but the ones you really want to remember are these triangles here, and I'll show you how these work. And what you should do, this is one of the things I recommend strongly, when you sit down to take a NABCEP test, they are going to give you sheets of scratch paper. And if you can learn to draw these triangles for yourself on that scratch paper as soon as they hand it to you, then you can refer back to them and you can answer questions based on them without having to think too hard if you have these in front of you. It's one of those things that can be very helpful. So if you can learn to draw these triangles for yourself on your scratch paper when you first sit down for the test, it will save you a lot of headache and make it more likely that you'll pass the test. So the way these triangles work is, I said it before, we know that amps times volts equals watts. And we can see that right over here. Volts times amps equals watts. And I've got it down here, volts times amps equals watts. And I know I'm saying it a lot, but I can't say it enough. So if we look at the triangle, we've got amps and volts equals watts. So I can multiply these two together and get watts. The other cool thing about this triangle is if I have watts and volts and I want to know my amps, what you can do is just cover up this A with your hand and you see it, watts divided by volts. And the other way around, if I have amps and watts and I want volts, I would cover up the V with my hand, and now I have my formula, watts divided by amps. Now the same thing works with this triangle as well. This is volts equals amps times resistance, which is another important formula. This is actually what voltage drop is based on for those of you who have gotten to calculate voltage drop. It's amps times resistance equals volts. So looking at the triangle, I've got amps times ohms is going to be volts. And if I have one and not the others, if I have ohms and volts but I don't have my amps, I can cover up amps with my hand here and then I'll see my formula, volts divided by resistance or divided by ohms. And then same thing, if I need to find out my ohms and I've got volts and amps, I can cover up the ohm symbol here and I see my formula, volts divided by amps. So these triangles can be very helpful if you can learn to draw them out for yourself and then learn to use them by covering up the one that you're looking for, and it will tell you what the, what to multiply or divide to get to that answer. So that's Ohm's law, and that's a useful little tool with these triangles to help you get through it. If you can memorize this whole wheel, go for it. But most people don't quite have that much brain space, and if you can do these two triangles, it'll get you through most of it.